So next we're going to talk about magnetic resonance imaging, MRI, and functional magnetic resonance imaging, fMRI. The first one, MRI, allows us to take structural images of the brain, so just imaging the anatomy of the brain. And then with fMRI, we can actually image function, so we can get a measurement of sort of what the brain is doing. Both of these techniques are newer than PET. So MRI, the basic MRI technology, was invented in the 70s. And fMRI is very new. So it was invented in the early 90s. And so in the course of the 90s, this type of research started to become more common. But the entire literature using fMRI is relatively new. So just something useful to keep in mind. So let's watch a little video from the NIH just as a warm-up.
MRIs use protons, which are abundant in the human body. All protons spin, creating a small magnetic charge. When a strong magnetic field is introduced, as is the case in an MRI machine, the protons align with that field. The MRI technician then introduces a radio frequency pulse that disrupts the proton and forces it either into a 90-degree or 180-degree realignment with the static magnetic field. Since the radio frequency pulse pushed the proton nature, once this pulse is turned off, the protons realign with that magnetic field, releasing electromagnetic energy along the way. The MRI is able to detect this energy and is able to differentiate various tissues based on how quickly they release energy after the pulse is turned off.
So here you learn about the large or the very strong magnetic field that is an important component of an MRI setup. And that's probably something that if you know anything about MRIs, you know that there's some big magnet that actually presents some safety challenges. But let's unpack a little bit. So first of all, our bodies are mostly water, and therefore they have a high concentration of hydrogen nuclei. And so the hydrogen nuclei normally point randomly in different directions. So something like that. But thanks to this very strong static magnetic field that is a component of an MRI lab, these nuclei line up in a parallel formation. So they all form something that we call an equilibrium. And the strong magnetic field in the MRI machine is it can be up to 80,000 times stronger than the Earth's magnetic field. So it really is something that you need to be highly aware of in an MRI lab. And in fact, it's very important that you don't have any metal with magnetic properties on your body, like a ring or something like that. Could just be sucked into the magnet and become sort of a missile. Okay, so we have this equilibrium. The equilibrium is only kind of a prerequisite for a clean signal. So now all these new hydrogen nuclei are nicely lined up such that when we then send out radio waves to disturb this equilibrium, we can observe the return of the hydrogen nuclei into equilibrium. And it's that return or the relaxation is what elicits the MRI signal. So as the hydrogen nuclei fall back into alignment, they produce a detectable radio signal, and the MRI signal decay rates are different for different types of biological tissues. And that's what provides us with that anatomical image that this type of imaging can yield. So for example, if you have tissues that contain little hydrogen, like bone, it will appear very dark on an MEG, on an MRI image, and then you get a lighter image for structures that have more hydrogen. So that is what basically yields this type of MRI image of the brain. So here we can see the black skull and then some lighter structures underneath. Okay, so this is just a picture of the brain. It does not actually tell us anything about what the brain might be doing. It just, in a static way, images the anatomy. So how can we then use the same technique to also get functional information?
Simply put, the magnet tracks hemoglobin, the iron-rich protein that makes your blood red. When hemoglobin transfers oxygen to your tissues, a tiny change occurs in the hemoglobin's magnetic field. So basically, when your brain cells call for more oxygen, this big brother can see it.
Okay. So here, we learn that fMRI is crucially based on the oxygenation level of blood. So let's delve into that a little bit. So blood is more oxygenated in an activated area of the brain than in a non-activated area. So when your brain is working hard, it wants more oxygen, and oxygen is attached to your hemoglobin. And when your hemoglobin is oxygenated, its magnetic properties are different from when it is not oxygenated or when it has less oxygen in it. So deoxyhemoglobin has a higher magnetization decay rate than oxygenated hemoglobin. And that is the fundamental property that fMRI is able to take advantage of and give us an image of where the brain is likely to be more active because of this higher demand for oxygen. There's a nice additional YouTube video here if you want to really get into the details more. But here's a simple visualization. So when we have high blood flow in an area, we'll also have more oxygenated hemoglobin, oxyhemoglobin, versus during normal flow or lesser flow, that will be a little bit less. So the most traditional way to analyze fMRI data is via the subtraction method. So here you have basically two experimental conditions. One of them is the so-called test condition. That's the process that you're trying to measure. And the other condition is a control condition, something that serves as some type of a baseline that you'll then compare the activation elicited by the test condition to. And so then you would perform a simple subtraction. So here, for example, if the test condition is just clenching your hand, so you're just eliciting basic motor activity, and the control condition is just rest, you're not doing anything, you would then subtract the fMRI activation of the rest situation from what is observed during the hand clenching. And that will then yield a statistical map, something like this, a little messy, and then you could overlay that with some thresholding into the anatomical image or the structural image that you would have obtained from your structural scan. So a typical fMRI session will involve both the structural imaging and the functional imaging, and they will have slightly different settings. Okay, so what are some of the pros and cons of fMRI then? So A major pro is that contra to PET, there's no need for anything like radioactive tracers. And for that reason, there's also no limit to how many fMRI scans you can undergo. So you can do like 3 a day if you want to. So it does not harm your body, or, you know, there's nothing to worry about in that sense. The spatial resolution is really good. So something like 3 to 6 millimeters in most situations. What are some of the cons then? Well, obviously the strong magnetic field necessitates strict safety protocols in a lab. So that's obviously something that you can overcome and address, but it is something that you always need to keep in mind. An fMRI lab is also, an fMRI lab scan is also very noisy. So it involves these on and off currents, and the on and offness of the situation causes these loud clicking sounds. You can listen to them here, but I'll give you a little demo. So if you're lying in the machine, here's kind of what you might hear. You get the idea. So now you can so this is a course about the neurobiology of language, so you can immediately imagine how, if you're, for example, interested in studying speech perception, then these loud noises would definitely cause a challenge. And so if the stimulus that you want to present to your subject, in fact, is auditory, you definitely need to be wearing headphones, like MRI compatible headphones, that will try to block most of this noise, and then give you a chance to give your brain a chance to actually appreciate the experimental stimulus. The temporal resolution of fMRI, because it's a hemodynamic technique, is not great. So it's in the order of seconds. So it's better than PET, but it's still too slow to, for example, characterize the detailed time course of linguistic processing. So that's something that we'll keep in mind throughout this course. So it is fast enough to distinguish between trials. So you can design an fMRI experiment where the trial types are mixed and not, as opposed to just blocked. So you just see the same type of stimulus for a while, and then the type changes. But it is not fast enough to distinguish between the activation patterns associated with different processing stages of a single stimulus. So for example, if you listen to a word and you take an fMRI image of the activations elicited by hearing that word, you will get just like a single image that represents all the different processing stages. So that's a limitation. So let's now look at the time course a little bit more. So you'll often hear the term hemodynamic lag. So that refers to the slowness of the hemodynamic response in response to the stimulus. So remember, with these techniques, we're not directly measuring neural activity, we're measuring a consequence of neural activity. So here's a visualization where we're imagining that A here is a little stimulus. So you could imagine that it's somebody saying cat, or you can imagine that it's a 100 millisecond tone or something like that, but it's some kind of a brief stimulus. And the subsequent line then shows you how say the bold signal would be developing over time. So there's a kind of a sluggish rise, so something like 6 to 9 seconds, and then there's an equally or even more sluggish return to baseline. Okay, and then that's even followed by something that we describe as an undershoot. So now you can imagine that if you're interested in responses to each stimulus, you would need to wait a long time before you could present the next stimulus. So if here's A, so let's just say that's like a high frequency tone, and you're interested in the sensitivity of auditory cortex to frequency, so you want to then like also present the low frequency tone. In principle, if you'd want to have a really clean recording, you would want to wait like this all this time before presenting the next stimulus. And that might not sound so terrible, but actually if you're an experimental subject and there's just a lot of nothing happening during the experiment, it's very boring to the extent that falling asleep is a real possibility. Okay, so what are then the different types of experimental designs that are available for fMRI? So here, the distinctions that I've alluded to are between the so-called blocked design. So here you really get the same type of stimulus for a while, then you would get like your fMRI image from that, and then the stimulus changes. You're not really worrying about time resolution because you're just kind of getting an image per block, say. And sometimes that's an okay thing to do, but a consequence of this type of stimulus presentation is that the subject becomes definitely very aware of what's going on. So if the contrast in these blocks, like let's just say in a language setting is a sentence with one type of structure versus a sentence with another type of structure, as a subject, you become aware of that, and that may actually affect your processing. There's also a repetition effect that would be very robust in this situation. So because those are all kind of not great properties for experimental design, we like to randomize trial order. So these are both cases of designs where trial order is randomized. So spaced mixed trial here refers to a situation where you're mixing the order, so you can't really predict what type of trial is coming next, but you wait for the hemodynamic response to return to baseline. So that's one type of a design that you'll see in fMRI studies. And so that's the design that's like pretty boring for the subject. But it is also possible to bring the trials closer together. But what that requires for fMRI is careful modeling of the way the hemodynamic response function accumulates if the responses kind of get overlaid on top of each other. So here in this situation, the hemodynamic response would not have time to return to baseline after the presentation of the first stimulus. The response to the second stimulus would somehow sit on top of that first response. But nowadays, we actually have a pretty good understanding of how those responses kind of combine, and that is making this type of experimental design possible as well. But it does really require that type of careful modeling. So those are some of the aspects of fMRI. Next, what we'll learn is that with electrophysiology, we don't need to really worry about this business between blocked versus rapid mix, etc., because we have this time resolution to record neural activity really as it's happening. So separating trials, even in this kind of rapid mixed trial situation, is not a problem.